Oh boy.
When I wake up each day, I feel so weary. Try to face the world, but it's so dreary. But I found that special thing that makes me cheery. Time to do music theory. Music theory.
You're watching Adventures in Music Theory with your host, Dr. Robbins. Hello. So here we are on the internet, ready to have us some 20th century theory. I think we can do this, and there's one sure way to find out, and that's by actually trying to do this. So let's pick up where we left off, talking about set theory and non-serial atonality. And we'll look at the piece that I gave you all for homework, the Webern 5 Movements for String Quartet. So I'd ask you all to go look at the Webern, listen to the Webern, I believe I said, and try to find some meaningful sets that might be worth pulling out. So that's always the hard part on this. What do you try? Well, I think one thing with this is maybe we try tetrachords. We try 4-note sets, because there are some in there that seem to be useful, like those chords in the violins, those tremolos at the beginning. Those are nice 4-note sets. Or that pizzicato chord that the violins play at the end of the second measure, or that little melodic lick in the first violin. Those are all things I might throw some lassos around. So there are 4 of them right there. And if you look at them and you take the set membership down, then the first one, the BCEF set, reduces to an 0156. And the second one reduces to an 0167. Maybe things will get more interesting. And they do. Look at the third one. It's that 0156 again, but now it's done as a pizzicato chord and not as a tremolo chord. And look at the fourth one. It's an 0167, but now instead of being a tremolo chord, it's a melodic line. So it looks like Webern is trying to do some stuff with his sets. And of course, once we know these sets, we can go ahead and get their interval vectors too. And one thing we notice when we look at their interval vectors, they're down there in the blue, is that their vectors are a little bit similar. You know, neither set has any whole steps or minor thirds. I guess IC2 and IC3 is what I should call them. But both sets contain 2 half steps, IC1s, and both sets contain 2 IC5s, which could be a perfect fourth or a perfect fifth. And each set has at least 1 tritone. So that means there's going to be a similarity of sound quality to those sets. And if we go on in the piece, you can look and see that he uses those 2 sets quite a lot in the first couple of systems. There are a lot of places where 0156 or 0167 show up. And there are, of course, fort set names for 0156 and 0167. They might be 4-7 and 4-8. I don't know. That's not an important thing. That's not something I expect you all to know, but feel free to look it up on that little fort sets appendix that I posted on Moodle if you want to. Now that doesn't explain everything in the piece, and we're not going to bother explaining everything, but there are some other things we might look at. Like, did you all notice that Webern had a little counterpoint moment around measure 5, where he's got the first violin and the cello playing in imitation? They both go C, F, D flat, C, D, C sharp. Sort of a little demented sort of early 20th century canon. So that's something you might look at set-wise. What happens if you put all those notes in a set? Well, C, C sharp, D, F becomes an 0125 set with that accompanying vector. And the other set that I think is really important in this piece is the one that happens in the second violin at the end of the second system there. It's a 7-note set, a heptachord or a septachord. Both names are used. If you look at it, you know, the nice thing to do is try to put those pitches in normal order. And this will make you work a little bit, because when you go to put those pitches in normal order, there they are stacked up in ascending order. It goes from B flat up to G. It's a major 6 tall, 9 half steps tall. If I put some numbers on it, it would be an 0, 1, 2, 3, 6, 8, 9. That's its normal order, but is it its best normal order? We don't know. We have to put it in inversion and see how it compares. We want the one that packs most to the left. And that inverts to 0, 1, 3, 7, 8, 9. So maybe the first version is the best normal order, or the prime form, since it ends 6, 8, 9 instead of 7, 8, 9. But not so fast there, because there's something funny about this set. That's maybe not the best normal order, because that set has its largest interval twice. It's got 3 half steps between G and B flat, but it's also got 3 half steps between C sharp and E. So maybe we should try stacking it that way. E, F sharp, G, B flat, B natural, C, C sharp. So we need to check that version of it as well. And that's an 0, 2, 3, 6, 7, 8, 9. That doesn't look as good as anything we've got up there. But when we invert that, we get 0, 1, 2, 3, 6, 7, 9. And that's the most left-packed version you can get. All the others end up 8, 9. This one ends up 7, 9. So that thing right there, that's the prime form. That's the best normal order. And Fort has some name for it that's 7-something, and I don't know what it is. But we want to find out some stuff about that set, because Webern uses it in the piece a few different times. In fact, he uses it every single time a section ends. He uses it at the end of the first section, and then there's that second section that has the pizzicato violin triplets and goes through measure 10, and then the viola plays that little 7-note melodic set. And then there's like a little echo of the beginning, and then the second violin plays that 7-note set again. So 0, 1, 2, 3, 6, 7, 9 as a set is something that happens fairly often in this piece. So this is a good example of how composers can unify a work without a tonal center by using recurrent sets. And all he's doing with that set is he's transposing at different times. The first one, we could call it T0, which has C on the bottom, and that makes sense anyway, because C is 0 and fixed 0 integers. And then when he plays it with the F on the bottom, when the viola does it, we could refer to that as T5. It's that first set transposed up 5 half steps. And when he plays it at the end with the G sharp as the first note, we could call that T8, because it's a version of the original set transposed up 8 half steps. And why not get a vector on that huge thing? So remember, to get a vector on that, we're going to put the numbers in the little triangle formation. And then we're going to go through and we're going to take all the 1s and 11s and put them in the first place on the vector, all the 2s and 10s and put them in the second place, all the 3s and 9s and put them in the third place, and so on and so on. And when we do that, we'll see that it makes this little repetitive vector pattern of 4, 3, 4, 3, 4, 3. And remember that you can use vectors to predict common tones under transposition. You look at a spot in the interval vector and it tells you how many common tones you'll have when you transpose up or down that far. So when I look at the 1 spot in the vector, it's telling me that if I go up or down 1 half step, there will be 4 common tones, because there's a 4 there. And the second spot has a 3, so that means if I go up or down 2 half steps, I'll have 3 common tones. So since the one transposition was T5, we'll look at the 5 spot on the vector, and we'll see that there's a number 4 there. I've got it bold-faced and underlined and stuff in the vector. That means there are going to be 4 common tones when we transpose it up 5 half steps. And if you look in the 2 sets at the top, you'll see that there are 4 letters that are written in red. Those are the common tones, right? It's showing that in T0 there's C, F, sharp, E, and B. And in T5, when we go up 5 half steps, there is still going to be a C and an E and an F sharp and a B. One of our other transpositions is T8. So that's going to be at the 4th spot in the vector, because transposing up 8 half steps is the same as transposing down 4 half steps. And it says there are 3 common tones when we go up or down 4 half steps. And when you look inside the original set and then the 3rd set down there, you'll see that there are 3 common tones. Both the original set and the version of it transposed up 8 half steps keep C and F sharp and G as common tones. Now here's something that shows the full score and shows a more complete look at some of the sets, though not all of the sets in the piece. But you can see that this is basically a work in ternary form, where that 3rd system, the a tempo part, is the B section through measure 10, and then the first measures and the last 3 measures are the A sections, and the B section creates contrast. And one way it creates contrast is by having different set forms. The A sections are characterized by 0156 and 0167 sets, but the B section has 2 sets that only occur in the B section, the 048 trichord that's played by the viola pizzicato, and that 0347 that the first violin's playing as the melody in the B section. Other interesting thing about these sets, there's a lot of symmetry. They're either inversionally symmetrical or transpositionally symmetrical, sometimes both. For instance, that 0156 set is inversionally symmetrical. If you invert it at inversion level 6, you'll get the exact same pitches. And the way you can see that is you look at the notes, you look at the numbers, and figure out what would I have to add to each of these numbers to get 6. So to add up 0156 and make each number equal 6, I would have to go 6510, the exact same notes. Likewise, the 0167 is inversionally symmetrical if you take it up 7 and invert and try to get everything to sum to 7, because when you want 0 to sum to 7 you get 7, when you want 1 to sum to 7 you get 6, when you want 6 to sum to 7 you get 1, and when you want 7 to sum to 7 you add 0. So that's going to be inversionally symmetrical. It's also transpositionally symmetrical. If you transpose it up 6 half steps, you'll get the exact same notes, right? 0 up 6 is 6, 1 up 6 is 7, 6 up 6 is 12 or 0, and 7 up 6 is 13 or 1. And you might be looking at going, well, wait a minute, why is the interval vector not telling me this? If I get 4 common tones, shouldn't the interval vector be showing me a 4? The answer is yeah, usually. And the reason this is the yeah, usually is because remember, in the interval vector, the number at the 6th spot is doubled. So if there's a 2 in the 6th place in the interval vector, that means you're going to get twice that many common tones when you transpose it up 6 half steps. And that's what happens, right? We take it up 6 half steps and we get twice 2 common tones. Now the sets in the B section, the 01347 is inversionally symmetrical at I7. Figure out what you'd have to add to each number beneath it to get 7, and you'd have to add 7430, which is the reverse of 0347. And then our 048 set, which is really just our augmented triad. It's only got major thirds in its interval vector, and it's symmetrical inversionally 3 times if you invert it at 8 or 4 or 0. And it's also transpositionally symmetrical if you take it up 4 half steps or up 8 half steps. So lots of symmetry from our buddy Webern here. Okay, and now let's try something different. Let's talk about inversion a little bit. And I'm going to show you all a couple ways to do it. One that's numerically based, one that's pitch class based. But I've got a little melodic line at the top there, and then I've inverted it on the 2nd system beneath it. And we're going to look at a few different ways you can invert that. Obviously, one way you can invert that is to just write all the intervals upside down. Instead of going up an augmented 5th from F to C sharp, you can go down that same number of half steps when you invert, down 8 half steps from F to A natural. And instead of going a half step down from C sharp to C, you go up a half step from A to B flat. You can do that. That'll take some time, but it'll work. I'm going to show you all some neat stuff though. And that little circle at the bottom with the clock face numbers around it is going to help us, especially when we start drawing lines and make it look like a basketball here in a second. When I inverted that first version, I started on F in both times, so I kept F in the same place, which is what that little red line is showing. But when I inverted the C sharp, it was no longer C sharp in inversion. It became A natural. So I'll draw a line across to show that. And the C natural in the original became a B flat in the inversion. And this is actually going to continue as we go on. The D sharp in the original, or the E flat if you want to think of it that way, became a G natural when we inverted. There's another line. And then we've already said C sharp is A. If you look at the B flat, it becomes a C. We've mentioned that already. C sharp is A. You know, if we keep going across though, we'll eventually get some new things to notice. Like if you look at the second to last note in this, it's originally an E natural. When we invert, it becomes an F sharp. And just to like go ahead and make our diagram complete, there weren't any B's or G sharps or D's, but if there had been, those B's would have stayed B's, and the G sharps and D's would have traded places. We call this trading places under inversion mapping onto, and we would say that at this inversion level, G sharp maps onto D, F maps onto F, and if you don't like the word maps onto, you can substitute the word trades places with. G trades places with E flat. So, you know, with a little basketball diagram like this, you can actually do this inversion a little bit faster. And it makes it easier if you want to like start the set or start the inversion on a different note. I started on F and had to think upside down then. And that was a little tricky. But imagine if I'd said start on A. Then you'd have to like start on a different note and think down all those intervals. And it could be tricky. But if you had this basketball diagram, it would be less tricky. F up 8 half steps is C sharp. A going down 8 half steps is C sharp. But what I've done is I've like changed how my basketball worked. In the first one, F stayed where it was. Now F has moved and traded places with A. And if I wanted, I could just go through and I could like draw the lines to show how everything's going to switch off there. And that tells me that not only if there's an F in the original, it's going to become an A. It tells me if there's a C sharp in the original, it's going to map onto itself and stay C sharp. And it tells me that the C natural is going to change into a D. And it tells me that a B is going to like take the place of the D sharp in the original set. And you can see how this map-on diagram can be helpful. Likewise, let's assume we wanted to start not on A, but we wanted to take the original one that started on F and started on E flat. So F and E flat are going to trade places. And my second note's C sharp, but when I draw the basketball lines across the thing, that C sharp is going to trade places with G, and that C natural is going to trade places with G sharp or A flat, as I've got it written there. And then of course that F and that E flat or D sharp trade off, and the A in the original becomes the B in the inversion, and you can see how that's going to work out here. And again, there are no D's or F sharp. Well, there is an E. The E is the second to last note in the original, and if you look, the E is also staying on itself, mapping onto itself. And even though there were no F sharps or D's, they would trade at this inversion level as well. So this is another way to think about inversion that you might find helpful. And it's not number oriented, it's pitch class oriented. So we still need to name our inversions sometimes, and that can be tricky. And there's a way to name them number-wise and a way to name them pitch class-wise. The number-wise way is the one that gives people trouble sometimes, because the way we think of transposition is very simple. If the original set's T0, when we transpose it up 2 half steps, we're going to call that T2. When we transpose it up 10 half steps, we're going to call that T10. With inversion, it doesn't work that way. The number for inversion tells us what numbers traded places and what they add up to, what the correspondence between them is. For instance, when I invert this thing starting on F, I'm going to call that I10 or T10I, depending on what terminology you like. And that's weird because, you know, you're sitting there thinking, but why are we saying 10? We didn't move anything 10 half steps. We started on F in both versions. It doesn't feel like we moved anything anywhere. Well, with inversion, we're not measuring how far we move stuff. We're measuring what trades places with what. And in this one, every note that trades places with another note adds up to 10. Like, for instance, we're going to use our fixed 0 pitch integers here. And remember, F is 5. So there was an F in the original, and when I inverted starting on F, there was an F there. That's 5. So we add those two together. 5 and 5 is 10. C sharp is 1, and it traded places with an A, which is number 9. And 1 and 9 is 10. You all know that. C is 0, and B flat is 10. So if you look, you'll see how every single note that's swapping up here, when you add it with the note above it, when you add their interval, their integer number, you get 10, and that's why we call this inversion 10. We do it differently with the pitch classes when we're not using numbers. Here's our inversion with the numbers again, the basketball. And when you're doing this, the way the inversion works is we simply call it letter name things. We would call this IFF, which means this is the inversion where F trades places with F. Technically, we could call it anything that's on the ball there. We could call it IFF, we could call it IF sharp E, we could call it IAC sharp, we could call it IBB. You know, they're all telling us the same thing. I just chose to call it IFF, but all those other names would fit as well. Now, if I was trying to put, no, let's look at another one here. Here's the one where like the F and the A switched places. And we would call that IFA, or we would call it IGG, or we could call it ICD. And it makes sense maybe to say IFA just because we're talking about our first pitch in the set. But again, they're all fine. And if we wanted to give it a number instead, we would call this I2. And the reason we're calling it I2 is because every number up there, when you add it as a fixed 0 integer, it's going to either equal 2 or 14. Right? F is 5, A is 9, that's 14. G is 7, and add G to itself, that's 7 plus 7 is 14. C is 0, and there it is trading places with D, which is 2. C sharp is 1, add C sharp to itself, that's 1 plus 1 is 2. So this is I2. And if you look at the next inversion we did, where the F and the E flat changed places, that of course is what we could call IFE flat if we're doing our pitch class thing. But if we wanted to like give it an integer name, then instead of saying IFE flat, we might call it I8 because everything adds up to 8. Right? F is 5, E flat is 3, 5 plus 3 is 8, C is 0, G sharp is 8, D is 2, F sharp is 6, that equals 8. So we can like also get our inversions from that. And chances are I might ask you to like show a little bit of facility with both of these on the test a week from Tuesday, meaning today if you're listening on Tuesday. Final thought about inversion and stuff. Here's a little set, and I'm going to show you all some things. I mean, one thing you all know is that we need to put these things in normal order. And one way we can do it is by using our fixed 0 pitches, saying A is 9, G sharp is 8, D is 2, C sharp is 1, doing it like that. And then of course we just put the numbers in some sort of ascending order. There it is, just starting with the lowest number going up, 1, 2, 8, 9. And of course that's not going to be a good normal order because when we look at that, you realize the biggest gap in the set is actually the 6 half steps from 2 to 8. So the high note of your big interval should be the low note of your set. So the 8 should be on the bottom. So it should be 8, 9, 1, 2. And if you want to turn that into like a generic set, you 0 it down and subtract 8 from everything to get 0, 1, 5, 6. Hey, I think we know that one, don't we? From Webern. And when we go to get our or transpose that, You don't even have to put these things in normal order to do it. Let's assume we were analyzing a piece, and that's the first version of that set we saw, and it was 98221. So we're going to call that T0 just because we got to it first in one particular analysis. If we want to talk about transposing it, well, if you transpose it up 2 half steps, you're going to call that T2. And the way you do it's real simple. You just add 2 to every note or every number in the set. So instead of coming up with 98221, you add 2 to all those and come up with 1110,443. That's transposition 2. And if you want to turn those into integers, you just write all the notes 2 half steps higher. Likewise, if we want to transpose it up 9 half steps, then we add 9 to everything, and it's all going to equal whatever plus 9 would be. So 9 plus 9 is 18, or 6 in Mod 12. 8 plus 9 is 17, or 5. 2 plus 9 is 11, and 1 plus 9 is 10. So the T9 version is going to be those numbers. 6 is F sharp, 5 is E sharp or F natural, 11 is B, and 10 is B flat or A sharp. So far fairly easy. When we start inverting this silliness, it gets a little crazier. But we're going to use index number thinking. We're going to have certain common numbers we always go with. For instance, if we want to do the I2 version of that, then what we need to do is figure out what's it going to take to make every single number in the original set equal 2, or 14. So to get 9 up to 14, you add 5. To get 8 up to 14, you add 6. To get 2 up to 2, you add 0. And to get 1 up to 2, you add 1. So the IT version is going to be 5,6, or the I2 version is going to be 56001. And of course we could see those as notes. 5 is F, 6 is F sharp, 0 of course is C, and D flat or C sharp is 1. Likewise, if we want to do the I9 version, then what you need to do is figure out, so what do I have to add to every note in the original set at the top of the page to equal 9? Well, you don't add anything to 9. You add 1 to 8, and you add 7 to 2, and 8 to 1. So your set's going to go 0, 1, 7, 7, 8. And 0 is C and 1 is C sharp. And that's what that particular inversion, the I9 inversion, is going to look like. So I'm thinking maybe a little assignment for us to do for Thursday would be good. And I want us to look at a piece that I think is really neat. This is from the third book of madrigals by George Crumb. It's a short song for soprano and vibraphone and harp. There are so many of those. And what I want you all to do is I want you to look in particular, this is a score from a paper I did and I've got some analysis on it. The sections I want you to look at most closely are the ones labeled A with the boxes. Look at the pitches there, especially in the vocal melody, and see if you can figure out something that's going on and if there's a way to describe them. You might find yourself drawing basketballs or doing things like that. It's hard to read the pitches because his scores are done by hand and they don't scan real well. So the version of it that I'm going to put on Moodle for you all to access, I'll actually write in the names of the pitches in the vocal line. So that'll help you a little bit. But let's look at that, and that'll be the subject of our discussion on Thursday, as well as any questions you all have in anticipation of the tests that will take place next Tuesday. So Thursday is for looking at Crumb and discussing about any questions you have about free atonality for the test on Tuesday, and I'll let you know what the format for the test will be as well. Until then, stay clean and safe and healthy and happy and well rested, and I will see you Thursday. And the video for Thursday, by the way, will be named April 2, 20th Century. Bye-bye.